Okay, so here's another question. It's not part of the notes, but it is felt another example could be beneficial for you. So a plane wishes to travel directly from A to B. B is 1,250 kilometers, 32 degrees east of south from A. So again, we're going to start by drawing a nice little compass somewhere on our page. I'll do it off to the side over here. So I know that's north, and to the right is east, south, and west. So east of south. So I'm going to start by drawing some point A. Here's A, and this is south. And east of south, so east is to the right of south, so it's going to swing over. So B could be, say, over here, for example. There's B. So our vector, our resultant vector is going to be from A to B. Okay, one of the hardest things about these problems is just being able to draw the scenario. So this is my 32 degrees. So in windless conditions, the plane has a speed of 555 kilometers per hour. So again, in real life, it's more complicated, but what we're assuming is that the plane is traveling at 555 kilometers per hour. If there's no wind, it's going to go directly from A to B. However, if there's wind, it's still going to travel at 555 kilometers per hour relative to the air, but because whether it's going against the wind or with the wind, it's either going to go faster or slower. Okay? So let's see, what is our wind vector? So the plane, so a strong 85 kilometer per hour wind blows in the direction of 60 degrees north of east. So I'm going to draw that vector just off to the side to make sure I understand what that means. So east is like that, right? And it's going north of east. So the wind vector is going to look something like the following. And there is my wind vector. So I know that my plane's direction vector plus the wind vector must add up to the resultant. So I'm actually going to draw in this one on my drawing first. So that wind vector is going to look something like the following right there. That's my wind vector. So that means in order for the plane to go directly from A to B, the plane must head at some direction of B. So this is the vector that the plane must face. So I'm going to redraw this just so it's easier for us to see. So here's so the plane head in this direction. So if I were to actually draw a little plane here, there's my plane. Oh, right. Here's my plane. Looks kind of like a fish. It's okay. So the plane's going to head in that direction. That's because the wind is going to push it back on course so that we can end up at B. So again, 8 and B. Alright, let's solve this problem. So let's see, fill in as many values as we can. So the plane has a speed of 555. So whatever direction the plane is facing, that vector is 555 kilometers. So this vector right here, this is going to be our 555 kilometers per hour. The wind has a speed of 85 kilometers per hour. I'm going to draw it off to the side because it's going to get a little busy. 85.0 kilometers per hour. So that's that vector right here. Let's see if we can add in some angles. So we already see that this angle right here, 32 degrees. We also know this 60 degrees north of east. So let's use this magenta color. So this angle right here, this is 60 degrees right here. So it can kind of be hard to see, but we actually have enough information to figure out some angles inside this triangle. So here is, let's see if you can see this one. Remember from math, if you have two parallel lines and another line that cuts across them, so I say this line and this line is parallel, we know that we call these alternate interior angles. So I know this angle with the dot is the same as that angle. I know that this angle with the x is the same as that angle. I know that this angle right here is also a dot because we call those opposite angles. So this is also going to be x. So maybe hard for you to see at first, but whenever you have one of these points, you can just imagine that x and y axes. It seems at this point, imagine that x and y axes right there. At each point, visualize those x and y axes. All of the y axes are parallel to every other y axis. So this line right here is parallel to this line over here. So we see there's that Z shape. So if this is 32 degrees, this must also be 32 degrees. Here's a triangle over here. That's 60 degrees. If that's 60, that's 90. This must be 30 degrees. So we actually know what the angle is inside this triangle right here. The angle on a line is 180. So 32, 30, and this missing angle is therefore going to be 180 minus 32 minus 30. We got 118 degrees inside this triangle. And now we can go ahead with the sine law. Let's do a sketch of this thing one more time because it can be hard to see this. So again, here's my starting, here's the vector for the plane, here is the wind vector, and here is my resultant vector. We just found out that this angle is 118 degrees. This is 85.0 kilometers per hour. And we know this is 555 kilometers per hour. And we see that 118 is opposite the 555 kilometers per hour. So we're going to do now sine law. So just going to solve for another one. For example, I say I want to solve for this angle right here. I can call that whatever I want. I'm going to call that phi. So I have sine phi over 85.0 kilometers per hour is equal to sine 118 degrees over 555 kilometers per hour. So what do we get for sine? You get a pretty small value because 555 is significantly greater than 85. So sine 118 divided by 555 multiplied by 85, and we get inverse sine. We get a value of 7.77 degrees. Now we can find some more angles. So for example, that's phi. What is this angle right here? Let's call that theta. Yeah, all the angles in a triangle add up to 180. So 118, 7.77. So 180 minus our previous answer of 7.77 minus 118. And we get theta is equal to 54.2 degrees. And now we can actually solve for the vector b. So we're actually wondering like what heading and to know what heading we actually need to know what speed as well. We actually know the heading right now actually. So how do we find the heading? We look back at our first diagram. We see that this angle is 32 degrees from A to B. We're trying to find out what angle must the plane face. So we're actually trying to find out what this angle is right here. So we just solved that for this angle is 7.7 degrees. So you get 32 minus 7.77. So our angle right there is 24.2 or 32 minus 24.2 degrees. 24 degrees. And we're almost there. So what is our velocity v? Let's use sine law again. We have v over the angle is 54.2. So sine 54.2 degrees equal to, we can use either of these other two. I like going with the stuff we knew from the beginning, just in case there was a mistake before. So we have 555 kilometers per hour over sine 118 degrees. So when we solve for v, 555 divided by sine 118 multiplied by sine 54.2, and we get a overall speed of 509.8 kilometers per hour. So we can write out our overall heading as the following. So 509.8 kilometers per hour, and our angle is, well, actually, sorry, we already know that angle is 32 degrees. So this is the current magnitude. So that's 32 degrees east of south. So this is the heading that the plane is. So even though the plane is pushing its engines to travel at 555 kilometers, because it's going slightly against the wind, its resultant speed is around 510 kilometers per hour at that 32 degrees east of south. That's the how long is it going to take. We know that d is equal to vt, and t is equal to d over v. But we need to use a corresponding distance and velocity vector. So we now know that 509.8 kilometers per hour, and we know that distance is 1250 kilometers per hour. So we can go 1250 kilometers, sorry, not kilometers per hour, kilometers. So 1250 kilometers divided by the 509.8 kilometers per hour. Now you can see that's going to take a total of 2.45 hours. So our final answer time is 2.45. Our overall heading was 24.2. So heading, we saw before by finding all the angles, came out to be 24 degrees. And that is also going to be east of south.